Welcome to Chapter 1, Section 12. We're going to talk about Python file operations in cybersecurity. Python uses the open function to work with files. We must also remember to close them. In cybersecurity, leaving a file open might lock logs or create opportunities for attackers. There are several modes we'll look at: read, write, append, and read binary. The The with open method is a context manager that is preferred since it closes files even if errors occur. This prevents resource leaks when working with sensitive logs or configuration files. As stated before, we're going to look at several modes to work with files. We have R for read logs, W for write, A for append, RB for read binary. We can use the read function to read the entire file, or we can use a loop to read files line by line. Writing to files lets us store findings or results. Appending ensures we don't lose earlier information, which is important for threat hunting data or generating log data. Let's take a look at an example of detecting brute force. We'll just start with the basics. Let's go ahead and click on or jump into our Kali VM, where inside our Kali VM I have an auth file here. So if we tail the auth log, you can see that there's some entries, and you see these failed password entries, which is something that we might want to take a look at. This could indicate a brute force attack. Let's go ahead and write some Python to read this log. I'll jump into Visual Studio Code, where I'll create a new file, and we'll call this brute force detector. Now, the first thing we need to do, there's 3 steps when we're dealing with files. We open the file, we do our processing, we close the file. Now, we're going to start with the old school way without using the with keyword, which is a context manager, and then we'll show you how to use the with keyword. We'll start with opening a file. We know that file is called auth.log. The next parameter is optional. This parameter, if we pass it, will be the mode that we want to use. By default, Open uses read only. So that's fine. We'll go ahead, and we need to create a variable, a target variable for our file object. I'm going to call that F. Now F, we can actually read the entire contents of a file. So I'm going to go ahead and do f.read and then f.close. These are the 3 steps to working with a file. We open the file, which returns a file object handle to the file. Then we read the data and do processing, and then we close the file itself so we don't have any type of resource leak. Go ahead and save this and jump into the terminal. And we'll use Python 3 to run our brute force detector. And you can see we didn't do anything. We just opened the file and closed it. So let's go in here and make a modification. Let's call this logs equals f.read, and then we'll go ahead and print logs. We'll run our brute force, and you can see it just dumps all of our logs to the screen. Now I want to show you what the type is on this. So let's print type of logs so we can show you the type. And let's go rerun our program here. And you can see it's just one big string with new lines. There's a better way to do this. We can actually read all the contents using read lines, which will read it line by line and stick them in a list. That will allow us to iterate over the lines. So I can jump back into the code here, and let's do lines. We're going to do read lines. I'm going to change my variable to lines, and now we can iterate. For line in lines, print line. This will show us that we'll have the same result here, but we're actually reading line by line. And you can see that we get this extra new line here because we're using the print statement. It captures the new line from the line itself in the log, and by default the print statement has a new line as a terminator. So you can actually see this is each entry is its own entry in a list. Now we can prove that this is a list by printing out lines, the type of lines. So print type lines, and we'll run this again. And at the top, before we print all the records here, we see that we have a list. Each entry is a log in there, and we can actually get the count of logs by just doing length of lines. So let's print the length of lines, save that, and you can see at the top here, once we get here, there were 201 lines in this log. All right, great. Let's go ahead and do some more processing here. Now let's change this. Let's use the width. So I can do, instead of this, width open auth log as F, and because we're using width, we can get rid of this close statement, and I can just do something like this. And this should work just the same. So we'll go ahead and save this and run this, and we need a colon because we're creating a code block. So let's put colon after our F, which is our target file, our target variable, I'm sorry. So let's run this again. And you can see it works just as expected. All right, so the next thing we want to do is do a little bit of string manipulation. We'll strip the line. And the last thing we want to do, before we print it, we want to check. So if we tail this, log again, you can see we're looking for failed password. So we see failed password in the log entry, then we're looking for, then that's something of interest. So we're just going to pull those out. So if failed password is in the line, then we'll print the line. And strip is a function, so we need two opening and closing parentheses there. That will strip the new line off, and we should have nice clean output. Oops, I tailed the auth log here. Oh, we have another failure syntax error. I need a colon since I'm creating a code block here. So we can use indentation for our code block. Go ahead and clear. And you can see, as expected, we get all of these failed password attempts here. And they look like they're coming all from pretty much the same IP address, or a lot of them are coming from the same IP address, which is an indication of brute force. So in future lectures, we'll continue to work down this example where we can actually identify possible IPs that are brute forcing our authentication mechanisms. Now, file operations come with risk. We must sanitize input for file paths, avoiding overwriting critical files, and safely handling binary malware samples without executing them. Also, when you're collecting user input, you should always sanitize user input, or there's possible attack vectors that you introduce into your program. So in conclusion, Python's file operations are invaluable in cybersecurity tasks. However, they must be handled responsibly to avoid introducing new vulnerabilities into your code. For the most part, if you're running scripts and you're just using them for yourself and not publishing them, you don't have to become over anxious about making sure everything works, that you're sanitizing all of your data. Once you start sharing it with others and you introduce vulnerabilities into your program, then that's where they can be capitalized on. Now it's your turn. We're going to give you a coding challenge. So in cybersecurity, verifying the integrity of files is critical for detecting tampering or corruption. One common method is to compare a file's calculated SHA-256 hash against a known good hash, often provided by the software vendor. Your challenge, if you choose to accept, is to write a Python program that prompts the user to enter the path to a file. Then it should prompt the user for a SHA-256 hash string to validate against. You'll need to read the file in binary mode and calculate its SHA-256 hash, and then compare it with the provided hash. It will print whether the file is valid or tampered with. Next up, we'll jump into Chapter 2.